We're going to examine part of the nervous system of the locust and try to find out how the patterns of certain nerve impulses are related to the insect's behaviour when threatened by a possible predator. It leaps for safety when stimulated by sudden movements in its vicinity. We shall examine the impulses which pass along a chain of axons leading from the locust's brain to muscles in its jumping legs. A large female locust is chilled in a refrigerator so that its activity is slowed down, but it isn't killed. A mount is prepared on which the insect can be held in position for the experiment with its ventral surface uppermost. It's stuck down using melted beeswax. Its legs are removed before it's put in position. There's one of the insect's eyes, and there's the thorax with the stumps of the 6 legs. These fine silver wires are going to be placed under a section of the ventral nerve cord, here, inside the insect's neck. Connection can then be made, along this cable, to the recording equipment which we shall see later. A piece of tape helps secure the locust. It's put under the dissecting microscope. Then small pieces of wax are placed against its neck like this. And they're melted into position, holding the head back. Another piece of wax on the other side. Now we're ready to begin the dissection. Tissue is very carefully cut away from the neck. Dry it out a little, and we expose the cervical connectives of the ventral nerve cord. The descending contralateral movement detector, the DCMD, runs inside these connectives. Now, one of the fine silver wires is placed in position under the nerve cord. It's pressed into the melted wax to hold it in position. Now for the second wire. This too is fixed down into the softened wax. We separate the wires so that they're not touching. And cover the wound with petroleum jelly to protect it from desiccation. Here's the experimental setup. There's the locust. It's placed inside an electrically screened cage, and the leads from the two silver wire electrodes in contact with the nerve cord are plugged into the display unit. Now electrical activity in the cord will be picked up by the electronic equipment. A preamplifier multiplies the current 1,000 times. And its output is amplified another 10 times and fed to this oscilloscope screen. The nerve impulses are also converted into sound signals heard from this loudspeaker. A second oscilloscope can store the pattern present at any given moment in time so that it can be examined. Just now, the locust's eyes are not being stimulated in any way. We're interested in this, its right eye. The oscilloscope exhibits the resting state, with no prominent nerve impulses showing. Frozen on the storage screen, it looks like this. We can slow down the scan speed on the oscilloscope so that we get this on the screen. And here it is as it appears on the storage screen. There are no large spikes in the pattern when the insect's eye is not being stimulated. We're now going to stimulate the right eye by making a shadow pass over it. See the characteristic indicating nerve impulses in the DCMD? Here they are frozen. Each spike represents what's called an action potential of about 2 millivolts in the neuron. The pattern's biphasic, a peak followed by a trough. Let's watch it at a slower rate of scan. On the storage screen, resting, we get no spikes. Stimulated, a clump of spikes. To investigate what's happening in a more controlled way, we use this continuous paper band, a kymograph. The paper passes across in front of the locust, which is here. And it's fixed at a known distance from the paper band. Here's the second drum on the right. We start it up at a set speed. And you can see that this has no stimulating effect on the locust. This is the pattern, in fact, for the resting state. But now we fix a black disc on the moving paper band which subtends a certain angle at the insect's right eye. This disc represents a 10-degree target. And here's the pattern of action potential spikes produced in the DCMD. Suppose the speed of the target spot is increased. We get fewer spikes. If the spots slowed down considerably, it's about to pass across the locus field of vision. Fewer spikes again. There's an optimum speed at which we get a maximum number of action potentials in the neuron. We can also vary the size of the target spots, keeping them all moving at the same optimum speed determined in experiments like the one you've just seen. This little disc subtends an angle of only 2 degrees at the locus right eye. And it produces very little effect. Again. Now for a 4-degree disc. A slightly greater effect. 6 degrees. Quite a clump of action potential spikes. 8 degrees. A more marked effect. 10 degrees. A quite large cluster of spikes. 12 degrees. Another large cluster. 20 degrees, a big disc. And less effect. There's an optimum spot size as well as an optimum speed for optimal DCMD response. For a thorough quantitative investigation, many runs are carried out, and each time the trace is photographed, like this, using a Polaroid camera. This is a run with the 10-degree spot. And we get a picture like this. Many pictures are taken. This is the little 2-degree spot again. Each disc is run several times with pauses between for the locus to settle down again. Here's its picture. We count the spikes on each photograph and from the data find out what is the speed of pass which most affects the locust and what is the optimum target size, somewhere in the mid-range of those we've been watching, like this taken from the 10-degree disc. We can also see evidence of adaptation, which is explained in the experiment booklet. The experiment booklet also gives data from such experiments, which you can now use to investigate the nature of the patterns of nerve impulse in the DCMD of the locust. Then you can try to relate this to the insect's escape response from possible predators. We're going to examine part of the nervous system of the locust and try to find out. There's one of the insect's eyes, and there's the thorax with the stumps of the 6 legs. These fine silver wires are going to be placed under a section of the ventral nerve cord here, inside the insect's neck. Connection can then be made along this cable to the out how the patterns of certain nerve impulses are related to the insect's behavior when threatened by a possible predator. It leaps for safety when stimulated by sudden movements in its vicinity. We shall examine the impulses which pass along a chain of axons leading from the locust's brain to muscles in its jumping legs. Experiment with its ventral surface uppermost. It's stuck down using melted beeswax. Its legs are removed before it's put in position. A large female locust is chilled in a refrigerator so that its activity is slowed down, but it isn't killed. A mount is prepared on which the insect can be held in position for the